In this set of videos, we're going to talk about the main concept and definition for Unit 2, which is about continuity. All right, so in this video, we're just going to look at the definition, and then in the next video, look at the different types of ways things can not fit the definition. All right, so the definition has three parts. All right, so if say a function is continuous at the point A, so it's going to take place at some x value, if all three of these things are true. So just being 2 out of 3 is not good enough. All three of these things have to be true. All right, the function value has to exist. So this means we have to be able to plug A into our function and get out some value. The limit has to exist, which means kind of the values close to A for our function makes sense. And then the last one is both those things exist. The last one is they're actually equal to each other. So really, this third one was really enough for the whole thing because they can't be equal if they don't exist, but that's kind of the three parts that go together. All right, both the limit and the actual function exist, and they're actually equal to each other. This is kind of like the best case scenario when your limit and your actual function agree. All right, if any of these are untrue, it doesn't fit the definition because the definition needs all three to be true. So if any of these are not true, we say the function is discontinuous at that x value A. All right, so if it's not continuous, it's discontinuous. All right, so let's look at this function. Rational function, weird things happen with rational, so we can talk about is it continuous at certain x values? So is f, this function, continuous at 1? Well, there's two things you need to check. The first thing is, what is f of 1? What is it and does it exist? Well, f of 1, we plug in 1 into our function. All right, so replace the x's with 1. And we get 3. All right, so when we plug in 1, we get 3. The other thing we have to do is check the limit as x approaches 1. All right, so same x value, x approaches 1 of x squared minus 4 over x minus 2. And what we saw in Unit 1 with a rational function is if you can plug in the value and you're not dividing by 0, then you can just plug it in. So this one, all right, we can just plug it in. And we actually already did this, we get 3. So both these exist, and you can see we get the same number. So is the function continuous at 1? Yes. All right, so pretty much if your limit ends up being the same thing as you just plugging in the number, then it's going to be continuous. All right, how about x equals 2? Well, then the first thing we have to do is figure out f of 2. And that's just when we plug 2 in. And here we get a 0 in the denominator. We know we can't divide by 0, so f of 2 can't exist because there's no way I can plug in 2 into this function. I'd be dividing by 0. So already that first part of the continuity definition is not true. So is it continuous at 2? No. All right, because we can't plug in 2. All right, we have to be able to plug in the value for f of 2 to exist. All right, what about this piecewise function? All right, g of x is equal to this piecewise function. All right, is it continuous at 3? Well, the first thing to do is check g of 3. And when I'm plugging in 3, I'm exactly equal, so I'm going to use this top function and just plug it in. That's 15 minus 2. That's 13. All right, so g of 3, if I plug 3 into my function, I get 13. All right, with piecewise functions, if I want to know the limit as x approaches 3, for piecewise function, I have to break it down into 2 pieces because I need to check both sides of this limit. So I need to check the limit of 3 from the left and the limit of 3 from the right. If those two things both exist and they're equal to each other, then that's equal to the limit, and then we can go from there. So the left-hand limit of g of x, I remember if you're on the left, your number is just less than 3, all right, just less than 3. So for the left-hand limit, I'm going to use the top part, which means I plug in 3 up there. I get 15 minus 2 again is 13. On the bottom, the right side of 3, that's when you're using numbers that are just greater than 3. If you're on the right side of 3, you're just bigger than 3. So I'm going to plug that into the bottom part. And that's 12 plus 1, and that's 13. All right, so we kind of work backwards from here. All right, we have our two one-sided limits. They're both equal to 13. So the full limit is also equal to 13. All right, so my full limit does exist and it's equal to 13. And then my g value, my function value is 13. My limit value was 13. So now I can finally answer, is this function continuous at 3? Yes. All right, so there's a lot of little steps and checks that go into making sure this is continuous. All right, but for this one, plug in the function value, or plug in the value into your function, you just get a number. Check the limit, and we did a whole unit on figuring out limits, so there might be some extra work like we did here. All right, but basically we get 13 for everything, which means it is continuous. All right, and just one thing, we'll talk more about continuity of an entire function in the next set of videos, but basically if I can draw this function without lifting up the pencil, in this case my Apple Pencil, then it's continuous. All right, as soon as I had to start doing things like putting holes in the graph or having jumps or having asymptotes that jump, all right, these are the things that are going to cause my function to not be continuous. All right, so if you can draw the function without lifting up your pencil or your pen, then it's going to be continuous. All right, so that's the basic definition of continuity. Try to remember there's 3 different parts and how to kind of figure out each one.